Thank you for the introduction, Leon, and thank you to the Deshpande Center for supporting our project. I am a postdoc under Dr. Mike Watts in the Photonics Microsystems group in the Research Laboratory of Electronics here at MIT. And I'm very excited to present to you today our work on commercializing silicon photonics for scalable Ethernet systems. Cisco predicts that by 2017, global Ethernet traffic will sum to 1.2 exabytes of data per month. Most of it's garbage. But this insatiable demand for bandwidth is reliably doubling every 18 to 24 months and has been for years. It used to be that data center traffic was predominantly from inside one data center out to another data center miles away. But today, with the advent of cloud computing and virtualization and Netflix binging, we now have a situation where data center traffic is now 75% internal. So most Ethernet packets never leave their originating data center. Today, the latest standard of 100 gigabit Ethernet has become the new workhorse technology and has supplanted all other previous standards. But the technology behind 100 gig is really bursting its buttons in terms of its ability to provide even more bandwidth. So to reach the next level of Ethernet, we will need a new technology such as integrated silicon photonics to come to the rescue, and let me explain exactly why. It used to be 10 or 15 years ago when bandwidth demands inside a data center were sub 10 gigabit, when we had two electronic digital integrated circuits that we wanted to connect together, we could just wire them together with copper wires. The problem with copper is that it has inherent resistance and electrical capacitance that creates a bandwidth bottleneck. So we can run it very fast, but it will take a lot of power. Or we can have it be very energy efficient, but it will be slow. So to overcome this bandwidth bottleneck, the industry has switched to using optical fiber. So this is the situation we have today, where we have an electronic digital integrated circuit, such as a network processor, and we've placed an optical module right next to it. This optical module allows us to go into the optical domain and use an optical fiber, which does not have this bandwidth bottleneck. The problem is when we want to go past 100 gigabits per second, this solution still has the same bandwidth bottleneck as the previous generation. Our solution to this problem is to integrate these two separate components together into a hybrid electro-optic digital integrated circuit. This allows us to have a high bandwidth, energy efficient optical channel from one hybrid integrated circuit to another one, and this is a distance insensitive link. It doesn't matter whether it's a few millimeters or a few kilometers, since we're using optical fiber. So our ability to integrate these two components very tightly is our primary innovation that we're looking to commercialize. And let me tell you exactly how we integrate these two. Our research group has collaborated with the foundry, and at the foundry, we manufacture a highly optimized optics-only wafer. At the same foundry, we manufacture a highly optimized electronics-only wafer. Then these two wafers get wafer-level bonded together using a technology called through-oxide vias. This approach is very economical. It supports very high volume manufacturing, and it's also very scalable as we move and shrink transistors to new process nodes. Silicon photonics is a very hot topic in the industry these days, and there are lots of efforts, both commercially and in research, for how we're going to combine both electronics and optics. Our approach allows us to separately optimize the photonics for extremely good optical performance, optimize the electronics at the same time for extremely good electrical component performance, and our approach allows us to have a fixed photonic cost. What that means is that as transistors shrink, the cost per millimeter is going up. But since our optics wafer is a separate wafer, the cost of optics will not increase as the transistor sizes are shrinking. Because we have such tight integration with electronics and optics, we have extremely good energy efficiency that other approaches don't have. So this all sounds very great, and I want to let you know that this technology is actually getting ready for commercialization. We have demonstrated it in our lab, and it does work. So some key milestones are that we've demonstrated the world's lowest energy modulator at 1 femtojoule per bit that we published in Nature Communication. We've demonstrated the world's largest integrated photonic circuit with 496 cells in a nanophotonic phased array, which we published in Nature in 2013. And just a couple of weeks ago at OFC, we presented the world's lowest energy electro-optic link at 250 femtojoules per bit. So this is clearly a disruptive technology, and let me show you how I think this is going to impact the current ecosystem of the supply chain. Our ultimate end user will be large data center operators, such as Amazon, Google, and Dropbox. These large data center operators purchase their routers from router manufacturers. The router manufacturers get their components from both chip manufacturers and optical module manufacturers. We imagine that this ecosystem is going to shift. We will partner with chip manufacturers to help them optically enable their existing network processors. These optically enabled network processors will then go upstream to the router manufacturers and then eventually to the end users. We're currently in the process of talking to both potential customers and potential end users. So if you have contacts in this space, please come see me at my poster. We have a team of several people who have years of experience in the silicon photonics space, led by Dr. Mike Watts, who's an associate professor here at MIT. We also have Jonathan Bradley, a research scientist, Michela Maresco, a fellow postdoc, and Erman, who is currently finishing up his PhD. So please come by my poster if you're interested in learning more, and thank you again to the Deshpande Center for your support.